today's agenda, we are going to finish up the notes for section 7.1, 7.2. There's just one more thing we didn't get to last week. And then we're going to jump into 7.3. Most of 7.3 we actually talked about way back in chapter 3. So for this first part anyways, it's going to be a lot of a review for you. Getting back into doing different calculations and things like that. And this is the chapter where you actually get to see why we did what we did back in chapter 3. I know a lot of you had questions at that point of why we were learning that. This is why. So I'm going to review it a little bit because it's been a while since chapter 3, and then we'll actually go into a lot more application of it. And when I get back, we are going to be doing a lab where you'll actually get to see where this all comes into play, where you really actually do use it in a lab setting. So that's the agenda for the day. I do want to remind you, I'm starting off on this slide to remind you that your naming practice worksheet, at this point you can do all but maybe, I don't know, 3 to 5 problems. And after today's class, you'll be able to answer every single problem. I'm going to give you some time at the end of class today to work on it a little bit, and then and feel free to work with a partner or so, no groups larger than 4 as always. And if you have any questions, hopefully you guys can help each other on that. And if not, it is due on Monday the 4th. But I will have office hours on that Monday, and it's a day 2, so I'll be in our classroom. So please feel free to come see me then. Or you're welcome to email me this week. Like I said in class last week, I'm not sure how much I'm going to have access to my email throughout the day, but I will try to get back to you as soon as possible. All right, so let's go ahead and get started. The last little piece of the section 1.2 notes is about acids and salts. And there are 2 types of acids. There's what we call a binary acid, and this is when you combine a hydrogen and a halogen. Remember, halogens are group 7 on the periodic table. That's your fluorine and your chlorine and your bromine and so on and so forth. So I gave you the example here in your notes of HF. So binary acids, remember the prefix bi means 2, so just 2 types of elements are combined here. Always a hydrogen, and then the second is always going to be a halogen, always something from group 7. The second type of an acid are oxyacids. And these contain hydrogen, oxygen, and usually a non-metal of some sort. Remember, your non-metals are to the right of the metalloid line, that stair-step line that goes through the right side of the periodic table. So an oxyacid is a hydrogen, an oxygen, and a non-metal. So an example of this would be H2SO4. You've got your hydrogen, you've got your oxygen, and then your non-metal, in this case, is sulfur. Notice that both binary acids and oxyacids, they both contain hydrogen. If hydrogen is at the beginning of the compound formula, that is an automatic indication of an acid. So if a compound starts with H, starts with hydrogen, it is always an acid. And it's only if it starts with a hydrogen. If hydrogen is somewhere in the middle or the end of the compound, not necessarily an acid. But if there is hydrogen at the very, very beginning, that is an automatic indication of an acid, which means that our most common compound that we've been talking about all year long, that you knew probably since grade school days, H2O, or good old water, starts with a hydrogen. Water is an example of an acid. Technically, water is an acid. It's a very weak acid, but it is an acid. Just look at the Grand Canyon. Water is what made the Grand Canyon. It ate away at the rocks and created that giant canyon. So anything that starts with a hydrogen, automatically an acid. And when we talk about acids, we also have to talk about salt. And salts are ionic compounds made from a cation and an anion from an acid. So an ionic compound made from a cation and an anion from an acid. NaCl, our table salt we always talk about, is made from the anion of hydrochloric acid. Hydrochloric acid is HCl. That chlorine is the anion, is the negatively charged ion in that compound. And when we break down hydrochloric acid, we get hydrogen and chlorine, and that chlorine is then used to create table salt. So in order to create table salt, the most common ingredient in almost every single food, in order to create that, you have to use a very, very strong acid for that. So any type of salt has to be made from the anion of an acid. So if we get any acid out there, break it down into its two pieces, its positive and its negative, you take that negative and that's what creates your acid. The most common acids are here in this table. You have them on your list, or in your notes I should say. And the ones that I want you to know off the top of your head, and on your test for this chapter, I'm just going to assume that you know these, are the ones outlined here in red. So take a moment to, whether you want to highlight them or put a star next to the ones that you're supposed to know, take a moment here and indicate which ones you need to know off the top of your head. So if the sub wouldn't mind pausing the video right now and giving everyone a moment to do that. Okay, so let's go over these just really quickly. I'm going to say them out loud so that you kind of know what it sounds like. So starting off, we have HF, hydrofluoric acid. That's one of our binaries. It contains only two types of elements, a hydrogen and a halogen, in this case fluorine. Then we've got HCl, which is hydrochloric acid, HBr, which is hydrobromic acid, and those are the three binary acids I want you to know. And yes, it is important that you put that acid word behind it. You can't just call it hydrofluoric or hydrochloric. You have to add the acid there. The rest are oxyacids. We have H3PO4, that's phosphoric acid. HNO3 is nitric acid. H2CO3 is carbonic acid. And H2SO4 is sulfuric acid. The last one I want you to know is HClO3, and that is chloric acid. Okay, so make sure that you know these particular ones. Okay, there's 8 of them that you need to know, and you just need to know these off the top of your head. You may already know some of them. You may already have known HCl was hydrochloric acid. So whether you make flashcards with these or just read them every day and they kind of get stuck in your head, but make sure that these 8 are the ones that you know just off the top of your head. And that's the end of the 7.1, 7.2 notes. So at this point, you can answer every question on that naming practice worksheet. Don't do it right now. I'm going to give you time at the end of class today to do that. But right now, you can do that. So that is going to be due on the 4th, the Monday after Derby, next Monday. Okay, so switch over to your section 3 notes for me, and we're going to go through a few things. And then you guys are going to do some practice problems on your own. Okay, so once everybody's switched over to the 7.3 notes, let's get started. First, a little review. When measuring individual atoms, we use AMU. Remember from chapter 3 we learned that AMU was a unit of measurement, atomic mass units. Atoms were so small that we didn't have any sort of unit that we could use, so scientists had to create one, and they created AMU. When measuring elements or compounds, we use grams. So when we have elements or compounds, that's a whole group of atoms. So since there's more of them, we can use grams. So what happens when we combine the two of these? So this question, what mass of copper, so remember copper is Cu, contains the same number of atoms as 26.98 grams of aluminum? So if we have 26.98 grams of aluminum, first we got to figure out how many atoms that's going to be, and then once we found out how many atoms that is, that same number of atoms of copper atoms, what's the weight of that going to be? Alright, so the first thing we got to do is to find the average atomic masses of copper and aluminum. So I'm going to switch over here to my periodic table, and I am going to find copper and aluminum. So if I look at my copper and my aluminum, and my pen is not working, hopefully, there we go. So copper, I look at this bottom number, the mass number, and I round it to 2 decimal places. So 63.546, I'm going to round that to 63.55. I'm going to do the exact same thing for aluminum. Aluminum, you have this big long decimal. I'm going to round it to 2 decimal places. So I'm going to round this to 26.98. So 26.98 AMU of aluminum and 63.55 AMU of copper. Again, AMU is atomic mass units. So what do these numbers stand for? What does this mean? This 26.98 AMU of aluminum and 63.55 AMU of copper. What does that 26.98 and that 63.55 stand for? Well, they stand for the mass of one atom of each element. So each element of aluminum, each element of copper, that is the mass of one atom. So the question of how many atoms of aluminum and copper do we have? Well, one atom of aluminum is equal to 26.98 AMU of aluminum, which we can then say, we can make the assumption, and there's this big long mathematical proof that shows this, but you guys don't need to know that, just take my word for it. If one atom of aluminum is equal to 26.98 AMU of aluminum, then we can say that aluminum is 26.98 grams. Okay, we can just make that assumption. So the mass number on the periodic table, if we change that from AMU to grams, they're equivalent to each other. Same thing for copper. One atom of copper is equal to 63.55 AMU of copper, which we can then say is equivalent to 63.55 grams of copper. So to answer our question of what mass of copper contains the same number of atoms as 26.98 grams of aluminum, well, if 26.98 grams of aluminum is equal to one atom, then one atom of copper would be 63.55 grams. Okay, so this is just answering that question of how do we get these grams? Because we can't really mathematically work with AMU. We really do need to work with grams. It's just easier mathematically. So this is the proof, the mathematical proof that allows us to make that assumption. So all we have to do is find that mass number off of the periodic table. And this is all leading us back into the mole. So hopefully this is starting to sound familiar. This is all review from Chapter 3, first semester. So first let's talk about what the mole is. If we weigh out all the elements so that their mass in grams is equal to their average atomic mass, then all the samples will have the same amount of atoms. So that mass of aluminum from the previous slide and the mass of the copper from the previous slide and the mass of hydrogen 1.01 and the mass of nitrogen, which would be 14.01, if you just go through that entire periodic table, each one of those, so the 1.01 grams of hydrogen, the 14.01 grams of nitrogen, the 16.00 grams of oxygen, all of those are actually equal to the exact same amount of atoms. If you counted up all the atoms in 1.01 grams of hydrogen, it would equal the amount of atoms in 14.01 grams of nitrogen, which is kind of a cool thing that works out to that fun little fact there, and we can use that very easily in all of our problems that we need to do. This number is called the mole. It's just, I don't honestly know why they called it the mole. They just named it the mole. And 1 mole is equal to Avogadro's number, and that number is 6.02 times 10 to the 23rd units. 1 mole is equal to 6.02 times 10 to the 23rd units. And we use the mole like we use the word dozen. You know, if I say I have 1 dozen, then that means that I have 12 of whatever it is that I'm describing. I have 12 units of that thing. So if I say I have 1 dozen donuts, I have 12 donuts. If I have 1 dozen donuts, I have 12 donuts. If I have a dozen pencils, I have 12 pencils. So if I have a mole of donuts, then that means that I have 6.02 times 10 to the 23rd donuts. That's a lot of donuts. If I have a mole of pencils, I have 6.02 times 10 to the 23rd donuts. The mole is a very, very large number. For example, a mole of seconds is 4 million times as long as the Earth has existed. The Earth has existed for about 4.6 billion years. So 4.6 billion times 4 million. That would be the amount of a mole of seconds. That's a lot. Okay, that's a whole lot. If we have a mole of marbles, we would cover the entire Earth, not just the United States, but the entire Earth from North Pole to South Pole, completely cover it 50 miles deep in marbles. That would be a mole of marbles. So from the ground to the sky would be filled with marbles, and that's about the distance from Louisville to Frankfurt. That's a lot of marbles. I don't think you want that many marbles. So the mole is this huge, huge number. So for normal, regular sized things, it's not a good thing to use. It's not a good unit of measurement. But for tiny microscopic atoms, it's great because they're so small, you can have a lot of them and it doesn't take up a lot of room. For example, this right here, picture, you also have it in your notes, is a mole of copper at the top, a mole of zinc, that's the second one from the top. I'm sorry, the second one from the top is iron, sorry. And then third is zinc, and the one at the bottom there is aluminum. And then there's a quarter there for size. So a mole of an element, a particular element, it's not that much. It's actually pretty small. And so it's great because atoms are so small, so we need this really big number to help us measure that. So now we are going to take a moment to watch this video, and there is a space in your notes that's just blank. It has the title of this, How Big is a Mole? And then there's an empty space there. That's for you to jot down some notes that you have learned from this video. So I'm going to stop talking and let the video play.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it. The story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Hopefully that video helped clear up some confusion and maybe gave you some visuals to think about when talking about the size of a mole, and how big and both how small it can be. I know we've been going for a while, and I promise we're just going to go just a little bit further and do some practice problems because, like I said before, it's been a little while since Chapter 3 and since that first semester exam where we did some of this stuff. So just hang with me for just a little bit longer. Let's do these practice problems, and then I will turn you loose to do some practice on your own. So, a sample of an element with a mass equal to that element's average atomic mass, expressed in grams, contains 1 mole of atoms, or 6.02 times 10 to the 23rd atoms. Now, I know that was a lot of words, but let's break it down just a little bit. So a sample of an element with a mass equal to that element's average atomic mass. So up here I've got the element symbol for gold, and gold's atomic mass is 196.97 because we always round to 2 decimal places. So if we put some gold on a scale, those little digital scales that we have in the lab next door, if we just kept adding gold onto that scale until the little digital readout read 196.97, at that point 196.97 grams, because that's what those scales measure in, then that would equal 1 mole of gold atoms. So that would be 1 mole of gold atoms would be on your scale there. That also means that there are a total of 6.02 times 10 to the 23rd atoms of gold sitting there on your scale. So the mass of the gold equal to its average atomic mass is equal to 1 mole, which is equal to 6.02 times 10 to the 23rd. So at this point, we know that, and this just breaks it down just a little bit further. It's exactly what I just said. You know, that looking at the gold on the periodic table and seeing that what atomic mass is in atomic mass units, 196.97. And so if we had that 196.97 grams of gold, we would have 1 mole of gold. So I've got some example problems. I'm going to switch over here to OneNote so I can write on the page. So what if it's asked me how many atoms would be in 0.500 grams of hydrogen? Well, first I'm going to come over here to the margin, and let's just write down what we just learned. Okay, so we just found out that 1 mole of any element is equal to its mass from the periodic table in grams. We also found out that that same mole is equal to 6.02 times 10 to the 23rd atoms. Hopefully this is ringing a few little bells here from chapter 3. This is exactly what we did in chapter 3. So one of these two is always going to be used. It's our conversion factor. Okay, so we have 2 conversion factors. They are what we use to solve all of these types of problems. 1 mole is equal to the mass in grams, and 1 mole is equal to 6.02 times 10 to the 23rd atoms. So for this first problem, it's given us 0.500 grams of hydrogen and asked for atoms. Well, if I look at my conversion factors over here, I don't have one that takes me perfectly from grams directly to atoms. But I can get grams to moles, and then I can get moles to atoms, which I know are your all's favorite problems. So we're going to start with putting this number that they give us in the problem in the top box. So I'm going to write down 0.500 grams of hydrogen, and I'm going to use my little boxes here because they help me stay organized and make sure I don't miss canceling out a unit of any sort. And I need to get to atoms, but I don't have a direct conversion factor between grams and atoms. But up here I can see that I do have one that takes me mass in grams is equal to 1 mole. So hydrogen, according to this little square right here, hydrogen has an atomic mass of 1.008. So that mass in grams is equal to 1 mole of hydrogen. So 1.01, I'll write it right here, 1.01 grams of hydrogen is equal to 1 mole of hydrogen. So that's what I'm going to put in my conversion fact, my boxes here. I need to decide though, where am I going to put that 1.01 grams of hydrogen? My choice is to put it on the top or the bottom of this line. I know that by the fact that grams is in the top box right next to it. If grams is in the top box, which it is right here, then that means that grams needs to be right here in the bottom box. So I put the 1.01 grams of hydrogen right here and the 1 mole of hydrogen right there in the top box. Now my grams have canceled themselves out, and that is why I always want to put them on opposite ends. And by doing that, that has left me with the only unit of mole. My numbers are still there. That 0.5 and the 1.01, those are still there. We just canceled the units, and that's it. So now I'm in moles of hydrogen, but that's not what they asked me for. They asked me for atoms. So I need to use the other conversion factor, the fact that 1 mole of hydrogen is equal to 6.02 times 10 to the 23rd atoms. So I'm just going to extend my line out a little bit. And since I have mole on the top, I need mole on the bottom. So 1 mole of hydrogen is equal to 6.02 times 10 to the 23rd, extend my line out here, atoms of hydrogen. So now moles cancel out moles, leaves me the only unit still standing is atoms, and that is exactly what they asked me for. So what I'm going to do now is I'm going to type this into my calculator. So as a little reminder, when we are typing in this 6.02 times 10 to the 23rd, what we're going to type in is 6.02 second, comma, 23. I don't type anything else but that. I'm going to type in second, comma, 23. Alright, I don't put a times sign. I do not put a 10. I don't put a caret. None of that. Just 0.5 times 6.02 second, comma, 23 divided by 1.01. Okay, so you multiply the top and you divide by the bottom. So take a second, find your answer. Alright, now if you typed it out incorrectly, you should have gotten 2.98019802 E23 on your calculator. Alright, but obviously we don't want to write all of that down on as our answer. So for right now, I know in chapter 3 we talked about sig fig rules and all of that stuff. I just want you to round everything at this point to 2 decimal places. Okay, so everything to the hundredths place. So if that is the case, that would be this guy right here. So we always look behind it. If this particular number is 5 or greater, we would have rounded up. Since it's not, we're going to keep it the same. So our final answer here is 2.98 times 10 to the 23rd, because that is what that E means, times 10. And we need a unit because all measurements have to have a number and a unit. And the only unit we have left is atoms of hydrogen. And that right there is our answer. Alright, let's do another one. How many moles and atoms are in 10.0 grams in a 10.0 gram sample of aluminum? Alright, so we always start by writing the problem that they give us in the top box. So we are going to say 10.0 grams of Al And yes, you do want to put the element symbol in there because trust me, later on we're going to need it in there, so it's good to be in a habit of it now. So we have 10.0 grams of aluminum, and they want both moles and atoms. And we know we can't go directly from grams to atoms. We know that from the previous problem, but we can go to moles very easily if we have the average atomic mass of that particular element, which that is what is right here at the bottom of the element symbol box. So round that to 2 decimal places, so that would be 26.98. Take a second, see if you can guess top or bottom. Hopefully you chose bottom because it is in grams, and we had grams at the top before, so they have to be on the bottom now, and that equals 1 mole of aluminum. So grams cancel out grams, leaves us with moles, which is one of the things they asked us for. So now in our calculator we're going to type in 10.0 divided by 26.98. We get a nice long decimal, but we're going to round everything to 2 decimal places. So we get 0.37 moles of aluminum. Okay, so you multiply the top, divide by the bottom. So 10.0 divided by 26.98, and that gives us a rounded 0.37. Now I'm going to leave that 0.37 long decimal answer in my calculator because I'm going to use that again in the next problem, because what they also asked us for is atoms. So I'm going to rewrite this 0.37 moles of aluminum, and I'm going to solve for atoms because our other conversion factor is the fact that 1 mole is equal to 6.02 times 10 to the 23rd atoms. So 1 mole is going to go on one of the sides, top or bottom. Think about it for a second. Hopefully you chose bottom because it was on the top from before. So 1 mole of atom is 1 mole of aluminum, is equal to 6.02 times 10 to the 23rd atoms of aluminum. So moles cancel out moles, leaves us with atoms, which is one of the things that they asked us for. Now in my calculator, I'm not going to retype 0.37 because I want to use that whole number that came before. So the last thing that I entered into my calculator was 10 divided by 26.98. And I hit enter, and I got a long decimal of 0.3706449222. That's still in my calculator. That was the last thing I entered. So I'm just going to go straight to my calculator because I want to take that number and multiply it by 6.02 times 10 to the 23rd. So I'm just going to pick my calculator up and I'm just going to write times. And if when I press times, I get on my screen A and S and then the multiplication sign. So it's taking that 0.3706449222, and it's going to take that whole thing and multiply it by whatever I type in next. So I'm going to type in 6.02, second comma, 23, enter. I get a long number. I'm going to round it to 2 decimal places, and I get 2.23. And if I look at the very end of the number, I see that E, which tells me times 10 to the 23rd atoms of aluminum. Okay, so I now know the moles and the atoms of 10 grams of aluminum. Okay, and go to the next problem here. Actually, I tell you what, how about right now we pause this and you with your table partners try these next 2 problems. The first is if you have a silicon chip that has a mass of 5.68 milligrams, check that, milligrams, so be careful there. How many atoms are present? And the next one is calculate both the number of moles in a sample of chromium containing 5.00 times 10 to the 20th atoms and the mass of the sample. Okay, so right now with your table partners, and if yours is missing, join a neighbor, try these two problems and then we'll go over it. So if the sub would please pause this video right now and give them a few minutes to work on these two. So for the first problem of if you have a silicon chip that has a mass of 5.68 milligrams, how many atoms are present? The first thing that we have to do is change those milligrams into grams, because where our conversion factors deal in grams, they don't deal in milligrams. So I used the conversion factor. 1 gram is equal to 1,000 milligrams. If you did King Henry, died by drinking chocolate milk, our little kind of cheat to get between units, that's totally fine as well. Yours is just going to be missing that first little set of boxes, that 1 gram and 1,000 milligrams there, and you'll just kind of start in with the next one. So you'll see with mine, I converted from milligrams to grams, and then from grams to moles using silicon's mass of 28.09, because you only want to round to 2 decimal places there, and then from moles to atoms. And then to solve that, I multiplied the top and divided by the bottom. So in my calculator, I typed in 5.68 times 6.02, second comma, 23, divided by 1,000, divided by 28.09. And I hit enter, rounded that answer to 2 decimal places, and I got 1.22 times 10 to the 20th atoms of silicon. For the second problem, you split it up into 2 like we did with that one example, and in the first one you are going to take those atoms, the number of atoms that they gave you, and you're going to divide it by the 6.02 times 10 to the 23rd. So in my calculator, I typed in 5.00 second comma 20 divided by 6.02 second comma 23. I rounded that number to 2 decimal places, and I forgot my box, but I got 8.31 times 10 to the negative 4th moles of chromium. For the second half of this problem, we take the answer we got from the first, write it down, it goes in the top box, and then we multiply it by that element's mass number, because 1 mole of an element is equal to its mass in grams. So for chromium, its mass number from the periodic table is 51.996, and if I'm going to round that to 2 decimal places, it rounds all the way up to 52.00, and yes, you do need both those zeros in there. So in my calculator, I still had the original answer from part 1, that 8.31 number, long decimal, so I just simply said, I pressed the times button, and on my screen it said ANS, and then that times key, 52.00, and then hit enter. And round that number to 2 decimal places, and you get 0.04 grams of chromium. Okay, so I want you to do some more practice with this. So if you switch to your mole calculation worksheet, I want you, for homework tonight, okay, and I am going to ask that the sub on Wednesday check this, I want you to do problems 1 through 8. Do the best you can. We're going to go over the answers next class, but please do problems 1 through 8 of the mole calculation worksheet. So at this point in class, you can work on one of 2 things. You can work on these problems from the mole calculation worksheet, or you can work on the naming practice worksheet, which will be due a week from today, next Monday, the 4th. So naming practice worksheet, that's due next Monday. This mole calculation worksheet, numbers 1 through 8, that is due next class. So prioritize as best as you can, And you can work on these two things for the rest of class today. Hope you're having a good one.